We are going to solve a problem based on principal stresses. So let me solve the problem now. Determine the maximum and minimum normal stresses and the maximum shear stress at the crankshaft bearing as shown in figure. So here the crankshaft bearing is given in the problem itself, the diagram is given. So we need to find the maximum and minimum normal stresses, then maximum shear stress. So these formulas will be in design data book, PSG design data book, page number 7.2. Maximum major and minor normal stress and maximum shear stress formula will be there in page number 7.2. And by calculating the stresses and substitute in the particular formula, we can get the normal stress and maximum shear stress value. Okay, let me see the diagram now. Here one side of crank web is given. So at that, this portion is known as crankshaft bearing and this one is known as crank pin. So at the crank pin, in the side view, this will be front view and this will be side view. And in the side view, they have mentioned the load value, which is 20 kilonewton, that is acting 45 degree to the horizontal. And we know that the dimensions given in the problem from the crank bearing to the web is 45 mm, thickness of web 20 mm, and then from the web to crank pin load acting point is 30 mm. So totally 95 mm. And the radius of crank is 175 mm. So based on the applied load 20 kilonewton, which is acting 45 degree to the horizontal, we have to calculate the stresses induced on the bearing. And the crank bearing diameter is 70 mm, that is given also. So we have to calculate the stresses and apply the stress value in the normal stress and shear stress formula to calculate the value. Okay, let me resolve the force first. And then after resolving the forces, we have to calculate the moments induced on the bearing and then we have to calculate the stress value one by one. So here there's a diagram. So additionally I have drawn the top view also to understand it easily. So here in the side view of crank web, this is crank shaft, one side of web is given in the problem itself. So only one side of the web is given. So this one is crank bearing and this one is crank pin. And here at the crank pin, the load is acting as inclined. So in the side view, we can see the load value. The load 20 kilonewton, that is acting 45 degree inclined. First we need to resolve it. While resolving the horizontal component and vertical component, actually the inclined force is moving left side downward direction. So horizontal component will be left side and vertical component will be downward direction. So we have to resolve it first. So the horizontal component, so here is a horizontal component which is acting left side direction. So if the angle is with horizontal line, the component will be named its cos. So 20 cos and 45 degree. The another component, that is vertical component, will be 20 sin 45 degree. So if the angle is mentioned with horizontal line, the component, that horizontal component is cos. So the angle, whichever line is mentioned with the angle, that line will be cos term. If the angle is mentioned with the vertical line, this one is cos term. So here the angle is mentioned with the horizontal line. So horizontal component will be the cos term. So 20 cos 45, the another term will be 20 sin 45. So that will be known from the force resolving in engineering mechanics. So you should see the video that is already in the playlist of engineering mechanics. Okay, fine. Here the inclined force 20 kilonewton, which is acting 45 degree, is resolved as horizontal component and vertical component. Horizontal component is 20 cos 45 degree, vertical component is 20 sin 45 degree. So let me denote with PH and PV value, horizontal and vertical load. And here vertical load is mentioned in the front view and the horizontal load is mentioned in the top view. So for that purpose, I have extended the diagram's top view also. Okay, fine. So for the given applied load, that is an inclined load, there are two different components and based on the components, different stresses will be induced. So first of all, let me see about the horizontal component alone. So number one, so due to horizontal component of stresses, so what will happen? So here is the horizontal component stress and this will be the vertical component stress. And here is the crank bearing, crankshaft bearing. So here if we consider the axis of the shaft and the horizontal load is acting, the shaft may be subjected to bending. So horizontal bending may happen if the horizontal force PH is acting on the crank pin. So here is the shaft. The shaft may bend in horizontal direction. So due to horizontal force, the first thing is there may be a chance of bending. So horizontal bending will be there. And then in similar case, if it is a bearing and this one is the radius, crank radius, and the horizontal load is applied, that may be a chance of turning moment also. So due to the horizontal force, there will be horizontal bending, and due to that kind of pedaling. So if it is an axis and here is the crank, if we apply the force horizontally like a pedaling, the entire crank may be applied by turning moment. So due to the horizontal force, there is a chance of shear stress due to turning. So the horizontal force may cause bending in horizontal direction. At the same time, it may cause turning moment at the crank bearing. And due to the vertical load, so due to the vertical load, which is PV, and here is the axis, the vertical load is perpendicular to the axis. So this may cause vertical bending of shaft. So due to the vertical load, there is a chance of bending, vertical bending. So we need to calculate three different stresses. So due to the horizontal component, there are bending stress and turning moment that may be cause shear stress. And then due to vertical component, there will be a vertical bending. That's it. So these three stresses we have to calculate, and we have to calculate the resultant bending stress. That's it. So bending stress and shear stress we need to calculate from the given loading condition, and after that we have to substitute in the normal maximum shear stress formula. Fine. So next thing, one by one we can calculate the value. So calculation of bending stresses. So due to the horizontal component and vertical component, horizontal component PH, which is 20 cos 45, this in kilonewton, so 20 into 10 power 3 Newton, and vertical component is 20 sin 45. So first of all, let me calculate the value of horizontal component and vertical component. So here 20 into 10 power 3 cos 45, which is nothing but 1 by root 2, and similarly 20 into 10 power 3 and the sin 45 value 1 by root 2. So cos component and horizontal component, vertical component, both are equal. Horizontal component and vertical component, which is 20 into 10 power 3. The angle is 45 degree, sin 45 and cos 45 both are equal. So the value of horizontal vertical component will be 1.414 into 10 power 4 Newton. So now we have calculated the horizontal component and vertical component force value, both are same. So let me calculate the bending moment created by the load. So PH value 1.414 into 10 power 4 and the perpendicular distance. So here the perpendicular distance will be, here is the horizontal component and here is the bearing. So this will be the perpendicular distance, which is 45 mm, 20 mm and 30 mm. So totally 95 mm. That is the perpendicular distance. So here is the force acting and here is the perpendicular distance to the bearing. So here bearing only we are going to calculate bending moment. So from that point to the load acting point, the distance is 95 mm. That's it. We can substitute here into 95 mm. So then the value will be 1.343 into 10 power 6 Newton millimeter. So force in Newton and distance in millimeter. So the value will be 1.343 into 10 power 6 Newton millimeter. And similarly vertical bending moment load. So we have calculated moment for horizontal loading. Now we are going to calculate for vertical loading. For vertical loading also the perpendicular distance will be same. That is 45, 20 and 30, 95 mm. So here for vertical bending moment, value 1.414 into 10 power 4, that is vertical load value, into distance, same distance, 95 mm. So the bending moment will be 1.343 into 10 power 6 Newton millimeter. So after calculating the horizontal bending moment and the vertical bending moment, we have to calculate the equivalent bending moment to calculate the bending stress value. So equivalent bending moment is equal to root of horizontal square and vertical square. So we can calculate the value 1.343 into 10 power 6 whole square, that is horizontal bending moment. And similarly for the same value for vertical bending moment, 1.343 into 10 power 6 square. So here by calculating the value of equivalent bending moment, the final value is 1.899 into 10 power 6 Newton millimeter. So that is the equivalent bending moment. So from the equivalent bending moment value, we have to calculate the bending stress. So by using the horizontal load component, vertical component, we have calculated the horizontal and vertical bending moment. And after that, we have to resolve it to calculate the equivalent bending moment. Using the equivalent bending moment, we have to calculate the bending stress value. So here bending stress formula is equal to MB by Z. MB is the equivalent bending moment, that has the value of 1.899 into 10 power 6 divided by Z value, that is section modulus pi by 32 d cube. D is nothing but at which the bending moment is acting. So here the bending moment is acting at the crankshaft bearing. So that has the diameter of 70 mm. So that diameter value D is equal to 70 mm. So by substituting that 1.899 into 10 power 6 divided by pi by 32 into 70 cube. So pi by 32 d cube is nothing but your section modulus Z formula for circular cross section. So now by calculating that, our stress value will be 56.4 Newton per mm square. So the bending stress value is calculated. And after that, due to horizontal component, there is a turning moment. So already we have discussed that due to horizontal component and vertical component, there will be bending stresses. So we have calculated the horizontal bending moment and vertical bending moment, and we resolved to calculate the sigma b value. And due to the horizontal force, there is a turning moment. So for that, we have to calculate the shear stress. That shear stress formula is equal to mt into r by j. That is turning moment into radius divided by j. We can simply substitute here. Radius is equal to diameter by 2. J is polar moment of inertia pi by 32 d power 4. And mt turning moment is equal to the force value due to the horizontal component. So we have to substitute the ph. So turning moment is equal to load into distance. So that distance. So due to the horizontal moment, horizontal force component, there is a chance of turning. So the turning radius will be the distance of crank radius. So which is nothing but 175 mm. So due to the horizontal force, there is a chance of turning. The turning radius will be the radius of crank, that is 175 mm. So that's what we are going to substitute. Fine. So first we can calculate the bending moment value. So first of all, we have to calculate the turning moment. Mt is equal to load value, that is the horizontal component, into turning radius 175 mm. So that is 1.414 into 10 power 4, the horizontal component value, into 175 mm. So which will be 2.4545 into 10 power 6 Newton millimeter. That is the turning moment value. And then we can substitute in stress formula. Stress is equal to turning moment 2.4545 into 10 power 6 divided by, so instead of r we can put d by 2. and instead of j we can put 3 by 32 d power 4. So that is 2.4545 into 10 power 6. See, diameter is nothing but the diameter at the turning moment will be induced, which is 70 mm. So 70 divided by 2 divided by pi by 32 into 70 power 4. So by simplifying that we can get the value 36.74 Newton per mm square. That's it. So now we have calculated the bending stress value and shear stress value. Using the calculated stress value, we have to apply in the normal stress and maximum shear stress formula. The data will be in page number 7.2, PSG design data book, page number 7.2. So here is the maximum and minor normal stress formula, and here is the maximum shear stress formula. If the formula will have plus or minus, if you substitute plus, you can get the maximum stress value. If you substitute minus, you can get the minimum stress value. Okay, now we can substitute one by one. And in the formula there are two stresses, stress along x direction, stress along y direction. So we have only one kind of stress, so we can substitute sigma y is equal to 0. We have only unidirectional stress only. So instead of sigma x we can substitute sigma b. For sigma y we have to substitute 0 because there is only one direction, another direction will be 0. And tau xy we have to substitute the shear stress value. And let me substitute here. Sigma 1 comma 2 is equal to 1 by 2, and the sigma x value, that is sigma b, which we have calculated, 56.4 plus sigma y value 0 and plus or minus sigma x value 56.4 minus sigma y value 0 the whole square plus 4 into tau value 36.74 square. That's it. And if you substitute plus, we can get the sigma 1. By calculating that, sigma 1 will be 74.51 Newton per mm square. And if you substitute minus, we can get sigma 2, that is minus 18.11 Newton per mm square. So from the normal stress formula, we have to substitute plus for maximum and minus for the minimum value, and we can get the maximum value, sigma maximum, which is 74.51, sigma minimum, that is minus 18.11. To calculate the maximum stress shear stress value, that is sigma 1 minus sigma 2 divided by 2. So sigma 1 is equal to 74.21 minus sigma 2 value minus 18.11 divided by 2. By calculating that, the value will be 46.3 Newton per mm square. That's it. So this is how we can calculate the principal stress value for the given loading condition. Thank you.